Okay, so we're talking about trig equations part 2, so using quadratic methods. So first I want to review the zero factor property. So I can demonstrate it with this example here, but I'll just quickly remind you what the zero factor property says in plain language. It says if you're multiplying two or more things together and they equal 0, then one of those things is 0. So in another way, if I have a times b equals 0, then that means that either a has to equal 0 or b equals 0. So this is so obvious in some ways that like you probably didn't even realize it was a property. But where this can be maybe slightly trickier is when you have to use it in a problem like this. So in this case, one of these things, this thing or this thing, one of them has to equal 0 for this whole thing to equal 0. So what that means then, from a practical standpoint, is I can take each one of these factors and set them equal to 0, and then I can just solve them like mini equations. So I'm going to get x equals -5 or x equals 3. So boom, that would be how you solve something from algebra using the zero factor property. But we can still use the zero factor property with trig. So now I've got cosine of theta times sine of theta equals 0 over this interval. All right, so what that means is the first function, well, either cosine or sine, one of those has to equal 0. So I break them up into two separate kind of factors and set each factor equal to 0. And then I just use the unit circle. So where does cosine equal 0? So cosine will equal 0 at either 90 degrees or 270 degrees, and then where will sine equal 0 either at 0 degrees or 180 degrees. So those are things that we just know, so I can write those down here. And so that's how you use the zero factor property. Okay, so next, let's try another example. And actually what I want to suggest here is that you try this one. So you can pause here, try it. You'll get more out of this if you try it, and then hit play when you're ready. Okay, so I've got my two factors, so you can see them separated by the parentheses. So I set each factor equal to 0, and then I can isolate the factors. So I need to figure out where cosecant of x equals -2 or cosecant of x equals square root of 2. And by the way, here's a little hack. You can invert these, so just flip the equations. So I know that so what I mean is, so cosecant and sine, those are reciprocals of one another, right? So if I want to write an equivalent expression, I can say sine of x equals 1 over -2. So see how I took the reciprocal? So I just like took the reciprocal of everything here. And I write, and then I can also do this here. So sine of x, so cosecant of x is square root of 2. So sine of x is 1 over the square root of 2, i.e. square root of 2 over 2. So I like to rewrite my factors like this just to help me look at the unit circle. So now I can just find, here's where I have sine is equal to -1/2, i.e. cosecant of x will equal -2. So they're one and the same. And then here's where I have my square root of 2 over 2. So I can see all my solutions here in radians. So then my solutions are 7 pi over 6, 11 pi over 6, 11, pi over 4, and 3 pi over 4. Okay, so that was the zero factor property, and now we can talk about quadratic methods. So I called it a property. I don't know why it's not really a property. But okay, so a lot of times what we do with quadratic methods is we can just factor, right? So I can factor this expression here, and then once again I'd set each factor equal to 0, and then I would solve to get x is -2 and x is -3. So I can pivot now, and I can do that same thing with trig functions. So I can also factor this equation here. So this equation factors as cosine x plus 1 times cosine x plus 1. Now, what if you're looking at this cosine squared x plus 2 cosine x plus 1? What if you're looking at this and you're saying, I don't know how to do this? There's a factoring hack you can use to help your brain figure out how something like this factors. So what you're going to do is you're going to let y equal cosine x. So notice everything in this equation is in terms of cosine x. So just set y equal to cosine x and then rewrite this equation. So now where I had cosine squared, I have y squared. Where I had 2 cosine x, I have 2y, and then the 1 just stays the same. So this I can look at and I can factor. My brain has no issue with that. So I factor this as y plus 1 times y plus 1. And then I just go back and I replace y equals cosine x to get this. So if you're having trouble looking at these and you're like, oh, I don't know how to factor these, just rewrite them. It's kind of a hack to convince your brain of how to do it. Okay, so anyways, so now I can set that, it's really just one factor, right? So cosine x plus 1. So I just have to figure out, where does cosine x equal -1? And so that will happen at 180 degrees. I feel like we know that at this point, so I don't even need the unit circle. Okay, so now what I want to do is I want to try another one of these, 2 cosine squared x plus cosine x minus 1 equals 0 for all possible solutions. So I suggest that you try this one. So remember, you won't get as much out of this video if you don't try. So pause here, give it a go, and then see how you did. Okay, so if you use that factoring hack, I could rewrite this as 2y squared plus y minus 1 equals 0. And ultimately, this expression will factor as 2 cosine x minus 1 times cosine x plus 1 equals 0. And so then I can set each one of those factors equal to 0, as you see here. And then I can finish solving for cosine of x. So I really need to figure out where cosine x equals 1/2 or where cosine x equals -1. So I can bust out my unit circle if I need to. So here are the x coordinates that equal 1/2. And for now, I'm just going to note the radians. So I know we need to do this for all possible solutions, but I'm going to just note kind of what these solutions would be on the standard unit circle. And then also here's where cosine of x is equal to -1. Okay, so that's the first thing that I want to notice. And the second thing I want to notice is there like a pattern between these? So the real pattern that you're looking for is if there's like a 90-degree difference between one solution and the next. In this case, there's no pattern like that. So since there's no clear pattern, what I'm going to do is I'm just going to use these 3 unique solutions as kind of the format for how my solutions should look. So I'm going to write these then as pi over 3 plus 2 pi n. So that would allow me to go, each time I go around the unit circle, 2 pi, when I land on that pi over 3 or its equivalent, then that's a solution. Same for pi and 5 pi over 3 plus 2 pi n. So just notice how I set that up. Okay, so let's keep going with this. Let's look at some other ways we could have to factor. So what about if I have 2 cosine squared x minus square root of 3 cosine x? So I'm doing this over 0 to 2 pi. All right, so once again, I'm going to suggest that you try here. I think you could do this totally on your own. This one's a little bit different, but give it a go, see how you do, and then hit play when you're ready. So, okay, this is going to factor as cosine x times 2 cosine x minus square root of 3. So notice in this case, we don't factor it like a trinomial. There's only 2 terms, but both terms have cosine x in common. Okay, so that being said, so here's how I've factored it, and then I can just set these terms equal to 0. So cosine of x equals 0, and 2 cosine x minus square root of 3 equals 0. Okay, so now I have, if I solve this one for cosine x, I get cosine x equals square root of 3 over 2. And now I can go through and just figure out what my solutions are. So where cosine of x equals 0, cosine of x is 0 at pi over 2 and 3 pi over 2, and then where cosine of x is square root of 3 over 2, that happens at pi over 6 and 11 pi over 6. So I can just note all those solutions as you see here, and that was the interval just from 0 to 2 pi, so we're done with this one. Okay, so let's try another one. Tangent x times cosecant x minus square root of 3 cosecant of x equals 0 for all solutions, and let's do this in degrees. Okay, so I would recommend that you try this one totally on your own. This one is a little bit tricky, so you just want to kind of think through the solutions, and then once again, just hit play when you're ready. Okay, so I can factor this as you see here. So I just factor out the cosecant. And so then, of course, I can set up my 2 factors, cosecant of x equals 0 and tangent of x minus square root of 3 equals 0. And so the key thing to think about with this factor here is, remember, cosecant of x is the same as 1 over sine of x. Can 1 over sine of x ever equal 0? No, it can't, right? So you can't have 1 over 0. That's not going to equal 0. So there's no other way to make this equal 0. So actually, for this solution pair, there's no solutions for cosecant of x equals 0. So we only need to focus on tangent of x equals square root of 3. And so looking at the unit circle, so I'm looking for those pairs that's going to give me square root of 3 just by itself. So that's going to be here at 60 degrees and then also at 240 degrees. And you can do the math. I've shown that in some other videos. You can do the math to just figure out that that will indeed equal square root of 3. Now, the thing that I want to point out here the thing that I want to point out here is that these two solutions, these are 180 degrees apart. So that's important to notice when you have to come up with the format for all solutions. So what we can do then is we can just say that x is going to be equal to 60 degrees plus 180 degrees n, and that's the format for all solutions. So yeah, you'll notice that, right? So every 180 degrees, I'm hitting a solution as I go around the unit circle. So that's kind of the idea behind that. So when they're 180 degrees apart, you want to take advantage of that. Okay, so I just want to go through a couple of tricky versions of this because, of course, you know, there's going to be a couple of tricky problems. So let's look at this first one. So cosecant squared x minus 2 cotangent x equals 0 over 0 to 360. Okay, so I want you to notice that there's no common factors, i.e. so it's not like I can factor this. So we're going to have to get a little crafty here. And so what I actually want to do in this case is I want to figure out how can I manipulate this equation so that I have everything in terms of one trig function. So I think about my Pythagorean identities, and specifically I think about how 1 plus cotangent squared theta equals cosecant squared theta. And so this is the identity that I'm going to use to help me rewrite this equation. So now I've got everything in terms of cotangent. So notice now I've got cotangent squared x plus 1 minus 2 cotangent squared x equals 0. So let me just write this in descending order because it's just better to look at. So I just rewrote it so that I can factor this. And this will totally factor, right? So you can pause the video here and try to factor this if you want. So this will factor as cotangent x minus 1 times cotangent x minus 1, and then we just solve as usual. So we got over that one tricky part, and now the rest of this is just smooth sailing. So now I just have to figure out where cotangent of x equals 1, and so I can refer to the unit circle. So that's going to happen at 45 degrees and 225 degrees, and so those are going to be my two solutions in this case. Okay, and so for the last problem I want to look at, so I've got tangent of x minus square root of 3 equals square root of 3 cotangent x minus 1 for all solutions. Okay, so the first thing that I'm going to do is, just to make this look easier to look at, I want to put the square root of 3's together on the same side, and then the 1, I'm going to put it with the tangent of x. I think it just makes it a little bit nicer to look at. And okay, so we have kind of the same problem that we did in the last equation, but so the goal is the same. So I want everything in terms of only one trig function. So I want everything in terms of tangent of x. However, there's no like nice way to, you know, use like the Pythagorean theorem or some identity to transform tangent of x into cotangent of x. So we're gonna have to be a little crafty here again, and I'm gonna show you what the trick is because I think this is kind of a tough trick. So what I'm gonna do is where I had cotangent of x, I'm gonna rewrite this as square root of 3 over tangent of x. These are actually equivalent to one another. But by rewriting this now in terms of tangent, now I can bust out another trick. So this is a fraction, and now that this is a fraction, I can clear the denominator of that fraction by multiplying every single part of the equation by tangent of x. So I multiply every single part by tangent of x, and so you can see what I get here. And so this just leaves me with the square root of 3. And so now this looks like something that's quadratic, so I can bring everything over to one side. And so now I've got everything over to one side, and I've set this equal to 0. And then, all right, what else can I do? Oh, so I've got tangent of x and tangent of x, so I can factor out the tangent of x to get this. So 1 minus square root of 3 tangent of x. Okay, so here's the deal. This guy here, this factors. So you might not have recognized that at first, and I think it would be really beneficial to you if you pause the video here and you try to factor this. So you try to factor this first, and if you get it, good, and if you don't, just hit play when you have tried at least 3 things. Okay, so this will factor as tangent of x minus the square root of 3 times tangent of x plus 1, and so now I can just, you know, do what I always do, so I set those factors equal to 0. So I'm looking for where tangent of x equals square root of 3 and tangent of x equals -1. So now let me just clear some space and let's look. So here's where we're going to have tangent of x is equal to square root of 3. And here's where I'm going to have tangent of x is equal to -1. And the thing I want to notice here, so these solution pairs, they are each 180 degrees apart. So I can really just have my solutions start at 60 degrees and 135 degrees, and then just keep adding increments of 180 degrees. And so I get the solutions that you see here. Okay, and so that brings us to the end of this video. So if this was helpful, please consider liking or leaving a comment. And otherwise, thanks for watching, guys. I will catch you in the next video.